In this video, we're going to take a look at how transition metal ions can form complex ions with various different ligands. Okay, so what does that all mean? Well, complex ions are something that consists of a central metal ion. So in our example here, we have Fe2+, which is our central metal ion, and it's surrounded by ligands. So what are ligands? Well, ligands can be various things. Basically, the main definition of a ligand is that it's either a negative ion or it's a neutral molecule, and it has to contain at least, and that's really important, at least one lone pair of electrons. If there are no pairs of lone electrons, it cannot act as a ligand. So some examples of ligands, neutral ones are things like water, NH3, or CO. So those are all neutral examples of ligands. Some examples of negative ions are things like Cl-, Br-, Cn-. So those are all examples of negative ions that can act as ligands. All of these have a lone pair of electrons that can interact with the positively charged metal ion. Now, in our diagram here is a water ligand, and water has two lone pairs of electrons on each oxygen of the water. And what happens to create these complex ions is the lone pair of electrons creates a coordinate covalent bond. So that means both electrons are coming from the oxygen, creating a bond with that iron metal ion in the middle. Okay. Now, in this example, there are 6 of them that are coordinating with this metal ion. And you can get various different coordination numbers in terms of creating these complex ions. So the iron 2 plus forming a complex ion with 6 ligands of water here is one example, but a couple of other examples. We have cobalt in the middle here, surrounded by 4 ligands of Cl-. We also have nickel here, surrounded by 4 ligands of Cn-. In terms of the shapes that these complex ions take, anytime you have 6 ligands, it's going to be an octahedral shape. So basically, it's following the rules of Vesper. So we have 6 things bonded to a central atom. It's an octahedral shape. It gets a little bit trickier when you have 4 ligands. It's a bit more complicated, so we're not really going to talk about that here in this video. But if you have 4 ligands, you can either have a tetrahedral shape, like the cobalt chloride complex ion here, or you might have a square planar shape. So those are kind of the 2 different shapes that you might see if it has 4 ligands. So just kind of knowing like there are different shapes of what these complex ions might look like. Now you can figure out oxidation numbers of the transition element in a complex ion pretty easily. And you do that by taking the charge of the ligand to figure out what the oxidation number of the transition metal is. So if we take a look at a couple of examples, in this first complex ion here, we have 6 water ligands in a complex with an iron. We need to recognize that the iron ligands are neutral, so they have a charge of 0. So that means that the charge outside here, that 2 plus, is going to be the oxidation number for our iron. So it's a +2 because we have 0 times 6, which is 0. So the only place that charge is coming from is from the iron. If we take a look at another example here, Cn, we need to recognize that it has a -1 charge. Now, because overall we have a negative 2 charge, if we call our nickel X, then we have X plus 4 times negative 1 is going to be equal to negative 2. Or X minus 4 is equal to negative 2. So X would need to be a plus 2. Or we would say that the oxidation number for nickel is plus 2 in this complex. So it's fairly simple to come up with the oxidation numbers if you know the charges on the ligands. Finally, the last sort of thing we want to talk about with complex ions is that they can be very, very useful as catalysts in different reactions. And the transition elements themselves can act as really good catalysts because they, one, have variable oxidation numbers. And then 2, they can form these complex ions. And the formation of the complex ions is key here in terms of its catalytic ability. So, for example, this sort of reaction shown in this diagram here is nitrogen plus hydrogen to form ammonia. This is something called the Haber process, and requires an iron catalyst in order for the reaction to occur. So what's kind of neat here is that you have molecules of nitrogen and hydrogen. They will dissociate, and then they will form complex ions with the iron catalyst that's on a surface here. It will bring those atoms close together so that they can react. And then once they've reacted and formed ammonia, they're released back out. So that becomes the product of this reaction. And if it wasn't for the fact that iron can form these complex ions with all the different things that are coming in, this reaction wouldn't be able to occur the way it does. So that is complex ions. How to look at their shapes, what they are, what they consist of, how to come up with their oxidation numbers, as well as how they are really important as catalysts in various different reactions. So that's it for this video. We'll see you in the next one.